2004. That's cooperation for Earth observation science, especially dedicated to the environmental and sustainable development. For example, aerosol, cloud, climate change effect. And for our universities, dedicated to the research on ocean environment production, use satellite technology for data retrieval and observation applications. So nowadays we are at the stage of Dragon 6, right? So Dr. Ulla Wandinger and myself are PI for this Dragon 6 program. So institute including the Leibniz Institute for Tropospheric Research, TROPOS, very famous institute for this in this field, and also Ocean University, and also includes the TROPOS, the German Aerospace Agency Institute of Physics, Atmospheric Physics, IPA, in Munich, and also NOA, National Observatory of Athens, Greece. And in Chinese side, we have CMA, Chinese Meteorological Agency, and NSMC, right? National Satellite Meteorological Center in Beijing, 卫星气象中心, and also Shanghai Institute for Fine Mechanics and Optics, Shanghai 光机所, Chinese Academy, and Lanzhou University, very famous for this atmospheric research. So this program is for 3 satellite research calibration and validation. First one is the very famous one, the ACTRlS satellite, which is first the wind LiDAR on board, on orbit. The second one is ACTRL 1号, that's the HSRL and the CO2 LiDAR for the first of this kind. And third one is EarthCARE, the LiDAR is the ACTRlS, which Ulla leading this program for the data retrieval and validation. So we now have 3 HSRL data LiDAR or有摄像头是吧 ？OK， 所以看的是我的。吴老师。Camera over here. So the program from 2025 for another 4 years this year. So we know Dr. Ulla Wandinger for a very long time, actually 10 years ago, at least 10 years. And Dr. Guang Yao, Dr. Dai is the first joint PhD students between our 2 institutes, right? 2016, right? 2016, oh, 9 years. So very good at strong, very strong connection between two. And we now very happy to have a common, another doctor candidate working on the EarthCARE and ACTRlS. So I think Dragon and other cooperation very useful things. So we have this long-term cooperation, especially for young scientists. We don't have analysts, we have Henry, so many. Because 20 years ago, I'm the young scientist of this program, actually. So very happy to have this reunion of this research family. So back to the topic of this morning. Dr. Ulla Wandinger will give a talk on one active sensitive aerosol cloud from ground and space. Dr. Ulla Wandinger is the leading scientist in Europe and worldwide for aerosol research, published the first scientific paper on Raman LiDAR method. Many people read the paper. So this year, we also will have a workshop on EarthCARE, right? So, and end of the year in Japan. So discuss the LiDAR and the radar and other spectrometers merged study. So I think it's just my first introduction. And on behalf of our institute and university, we have a little present for you and a different guest. So you already see. Yes, please. I have this one. You did. Okay. Okay. Yeah, it's a plate. I think the centers of our university, and it lasted for, I think exactly it's 100 years ago, 1924. You can see it's very similar stuff. Fishman's campus at that time. So, sure. And also we have another tool for our young scientists. Yeah, please. Okay, so I think we gave the floor to Dr. Ulla Wandinger.
Yeah. Okay.
You can use this one. No? Okay.
Okay. Good morning, everybody. It's a great pleasure to be here, and thank you for the invitation. We had already 3 days here in Qingdao, very nice city at the ocean side. We had a very good symposium and talked a lot together. And now I try to introduce a little bit what we do in Germany regarding aerosol and cloud remote sensing. So the outline of my talk, I will give a little bit, try to give a global view on aerosols and what we can do to sense aerosols and clouds at the global scale. I will talk a little bit about the principles, maybe many of you are familiar with. And my focus will be also a bit on the wildfire smoke as one important aerosol that nowadays in the atmosphere. And I will give also some perspective on synergistic observations that we can do by combining LiDAR techniques and also LiDAR and radar together, and we'll end with some take-home messages. So if we look at our from the space, we first of all see, of course, the clouds. The aerosols are a little bit hidden, so we need a more focused view. But you can imagine most of the Earth is ocean surface. It produces sea salt as a natural aerosol. We may have volcanic eruptions which produce ash and sulfate aerosol. We have a lot of deserts producing mineral dust and bringing that into the atmosphere. We have wildfires producing smoke. And we have plants, forests, for example, which emit gases and in this way also precursors for biogenic particles. So this is what is natural, and then we have our anthropogenic contribution from the emissions from the industry, from the traffic that also contributes to the atmospheric aerosol load. The aerosols are processed in the atmosphere. They are transported often over very wide distances. They interact with each other. They interact with clouds and with radiation. And so we have to deal with clouds and precipitation. We have to deal with air quality and health issues. And we need to understand the radiation and the dynamics in the atmosphere to completely understand what role aerosols in the atmosphere play. So, of course, we would like to look everywhere on Earth. We can do that from satellites, but satellite view is often not so well solved. so we should also look from ground where we can understand the processes much better. And this is our intention, what we do in our institute at TROPOS. We use mobile LiDAR systems to go into different regions of the world to investigate aerosols. And you see we have permanent stations like on Cabo Verde in Europe, in Central Asia. And we have a lot of field campaigns where we bring our systems into key regions of climate change to investigate aerosols, for example, in the Arctic region, in the Antarctic region, in the rainforest, in the southern hemisphere, in the northern hemisphere. So to get a global view and the global understanding of the aerosols. And we do this with our poly system. So poly is a mobile system which we use. We have like 10 to 15 of them in operation. And you see this is a multi-wavelength Raman polarization LiDAR. It uses a neodymium laser to emit the usual LiDAR wavelengths of 355, 532, and 1064 nanometers. And then we have many receiver channels where we receive the elastic backscatter. We receive a molecular backscatter, the cross-polarized component of the light, and water vapor signals, for example. So we get a lot of information with these systems from the atmosphere. These systems are fully automized, so we can operate them remotely and also transfer the data via the internet. This is our workhorse, which we use. And you can find more information on our so-called PolyXD, which stands for Portable LiDAR System Extended. There are some papers listed here. And this is some impression how it looks like when we go into the field with the poly. We have some permanent stations in Israel, for example, in Finland, in Dushanbe. We had field campaigns in the rainforest in Manaus. We have our permanent station in Cabo Verde. This was the field site in Punta Arenas, Chile. So you see a lot of different landscapes, lot of different surroundings, environments where we can investigate the aerosol state of the atmosphere. The PolyNet is fully integrated in the European research infrastructure, so it is part of EARLINET, the European Aerosol Research Lidar Network, and the ACTRlS infrastructure. So ACTRlS stands for Aerosol Clouds and Trace Gases, and it is now established as a permanent observing infrastructure in Germany. You see, for example, here all the stations. They are not only for aerosol measurements, so they measure aerosols remotely and in situ, but also clouds and also reactive trace gases. So this is the big observing network with about 75 distributed stations in Europe and also in other locations in the world. The red circles indicate where we contribute with our poly systems to EARLINET and to ACTRlS. So we have several ACTRlS stations equipped with poly LiDARs, not only operated by our institutes, but also operated like by the National Observatory of Athens, by the Cyprus Center of Excellence, Eratosthenes in Cyprus, by the Finnish Meteorological Institute. So there are several partners involved in the operation of the PolyNet LiDAR. And then PolyNet is not the only instrument that we run. It's of course the workhorse for the aerosol observations, but we also try to integrate it in our bigger mobile systems, and we have two of them. This is LACROSS, it's the Leipzig Aerosol and Cloud Remote Observation Systems, and our OceanNet atmosphere facility, which are put into containers so we can transfer them and put them in different locations. LACROSS is mainly for land-based applications, and OceanNet atmosphere for the shipborne applications. And you see there are a lot of instruments. Maybe it disappears again. So we have combined with the LiDAR, we have radar systems. After 34 gigahertz cloud radar and the 94 gigahertz cloud radar, we have the microwave radiometer, we have rain radar, we have photometer, ground-based measurements, in situ measurements, the discometer to measure the rain rate, the spirometer, so a whole bunch of instruments which allow us to look into the atmosphere and observe aerosols and clouds in a very sophisticated manner. And you see here applications for our shipborne system. The OceanNet atmosphere has often gone with the German research vessel Polarstern, but also on other research vessels. We have the Sonne and we have the Meteor, so 3 big research vessels in Germany where we can put our containers on and go across the oceans with this system. And this shows another application. This is our Antarctic campaign, and my colleague Martin Radens spent more than 1 year at the German Antarctic station Neumayer 3 and took our mobile system there and took care during the Antarctic winter of all these instruments. It was a very great effort, and yeah, we got very nice observations in Antarctica with this system as well. So to come back a bit to the theory, I don't know how many people are involved in LiDAR research here and know the LiDAR principle. For those who are not so familiar with, I can explain briefly how it works. We use a pulsed laser to emit laser light into the atmosphere where it is scattered by molecules and by different particles and cloud hydrometeors. The light is backscattered to the LiDAR receiver on the way into the atmosphere, and on the way back it is also extinguished. So we have information on the backscattering properties of the atmosphere and on the extinction properties of the atmosphere, because the system is pulsed. We can measure the travel time until we receive the backscattered light, so we get the range-dependent measurement by knowing the speed of light in the atmosphere. This you may be familiar with, the Raman LiDAR principle. I put here one of our very first measurements on the left-hand side. You see a measurement from 1989, 24th of October. When we first put the Raman LiDAR system into the field, this was on the island of Norderney in the German North Sea, and it was the first time we could demonstrate that we can measure backscatter signals together with Raman backscatter signals from nitrogen, and you nicely see what happens if there is an object, a target in the atmosphere. You get the increased backscatter in the electric signal, and in the nitrogen signal, you see only the extinction, because the molecules make the backscattering. The molecules are known in the atmosphere, and from this signal we can derive the atmospheric extinction. And so we get to the independent measure of extinction and backscatter, and the ratio of the both is called the LiDAR ratio, which is an intensive property of the target, so it tells us something about the properties of the target. On the right-hand side, you see the spectrum that you use. The laser light is emitted at 355 in this case. Elastic backscattering, we have rotational Raman lines to the left and right. And we have vibrational, rotational Raman lines from oxygen, nitrogen, and water vapor, which we can use for our investigations. And usually we use nitrogen signals to obtain the extinction coefficient. And so this is already well-established methods dating back to the 1990s, which you can also find in the Springer textbook. And what we use in addition is the polarization. So we emit linearly polarized laser light, and we measure the backscattering. We solve it for the cross-polarized component and the parallel polarized component, and in this way we can measure the depolarization ratio. And the depolarization ratio tells us something about the shape of the particles. So if the particles are spherical, we measure no depolarization. If the particles become non-spherical, like for mineral dust particles, for example, or for ice crystals in the atmosphere, then we measure a certain depolarization. This is just an example. It is a measurement over several days from the 19th of April to the 24th of April, 2017. It's made in Cyprus, and we had a big Saharan dust outbreak lasting over several days. And this is the backscatter signal, what you see on the top, and in the bottom you see the depolarization ratio. And you nicely see these strong depolarization, what you get from the dust. So, for example, the marine boundary layer mainly consisting of spherical particles, spherical sea salt particles. You see the marine boundary layer in the backscatter, but in the depolarization, you don't see much depolarization. You see the depolarization from the ice clouds and, of course, from the dust. Do you see an animal in here? For me, I always call it my Red Bull example case. So it's a little bit of fantasy you may. So now, if we go more into the details of the measurement, so for this period, what is indicated here, I extracted the profiles, and this is what you usually get. You see on the left-hand side, you get the three backscatter coefficient profiles, the marine boundary layer below 1 kilometer, and then the dust layer above with a strong contribution between 3 and 5 kilometers here. Then we measure the extinction coefficient. This comes from the Raman signals in the blue and in the green wavelength range. And we measure the LiDAR ratio. And then the Angstrom exponent, this gives us the wavelength dependent. We can do this for extinction and for backscattering. And the right one is then the particle linear depolarization ratio. So you nicely see the properties of the dust. So the extinction is almost neutral. So the Angstrom exponent is close to 0 in this case because the particles are large. LiDAR ratio is around 50 for dust, and the depolarization is a bit higher, so between 25 and 30%, and between 20 and 25% in the blue. So these are very typical values for the dust layer. So you see the mean values for this layer here from 3 to 5 kilometer height, LiDAR ratio between 45 and 50, and depolarization ratio between 20 and 26. So when you do a lot of such measurements, we can come to some conclusion how we can characterize the different particles in the atmosphere. So we have the Angstrom exponent, you have the LiDAR ratio available, and you have the depolarization ratio available, and we can distinguish these different kinds of aerosols. For example, we have small and absorbing particles like pollution particles, which contain soot or biomass burning, for example. When they are small, it means the Angstrom exponent is high. The LiDAR ratio is high because they have a lot of extinction in addition because of absorption, so you get a high LiDAR ratio, and the shape is, the particles are small and they can be considered as small and spherical, so depolarization is low. For the mineral dust, this looks different. The Angstrom exponent is close to 0, LiDAR ratio around 50, and we get a high depolarization ratio. And if in contrast, we have also large particles, but they are spherical, like for sea salt, then the Angstrom is similar as for the dust, but the LiDAR ratio is much smaller, and also the depolarization is close to 0. So we can, by using these intensive optical properties, so independent of the concentration of the particles in the atmosphere, we can distinguish the different kind of particles very well. And if we bring all our observations together, we can put this in such a two-dimensional diagram where we plot the LiDAR ratio against the particle depolarization ratio, and the different colors indicate different kinds of aerosols in this diagram. And you see here in the legend, these are all our different field campaigns and also permanent observations we do in the different locations. And you see like a pure aerosol type, like the pure dust has a very high depolarization ratio, but you also see the field dot, this is the Saharan dust, while the open dot here is Asian dust. So we can also distinguish different types of dust in this way. We see clearly the marine particles in the lower left corner. We see the smoke in the upper left corner, and in between the pollution. And then we have different kinds of mixed states where we can have, for example, mixture of dust and pollution, or dust and smoke, what you typically see in the region, in the outflow of Africa, when the biomass burning smoke is mixed with the dust coming from the Sahara, then we see also these kinds of mixtures. And we make use of this to distinguish the different aerosol types. So you see again a summary here of all our investigations worldwide, includes also measurements in the Pearl River Delta that we made in the early 2000s. Now with all this knowledge, with this deep investigation we get from the grant, we can also transfer our knowledge to the spaceborne observations. And I have put here the different missions we had since 2006. It started with Calypso, and we had Olos, we have the ACTRlS LiDAR on the Dutch G1 satellite from China since 2002, and we have EarthCARE since last year. And with our knowledge on the aerosols and on the aerosol typing, we can apply this also to spaceborne retrieval now. Summarizes again the four missions that we have available over the last 3 decades for active aerosol remote sensing from space. But what you also see is we use different techniques in these different missions. So Calypso worked at 532 and 1064. Then we have Olos, the Aladdin LiDAR, and the ACTRlS LiDAR, HSRL LiDAR, high spectral resolution LiDAR looking at 355 nanometers, and we have the ACTRlS, a high resolution LiDAR looking at 533 nanometers, and having also a backscatter measurement in the infrared. So we also need this knowledge on the wavelength dependence of the aerosol gathering to bring these different observations together and get a kind of harmonization. And this can be done via the aerosol classification. So if we have all this knowledge about the aerosols and the different types, then we can also relate these different measurements in the long term to each other. And to emphasize again why it is important to use the high spectral resolution LiDAR technique. So HSRL, this is very similar to the Raman LiDAR technique. So you make use of a molecular backscatter signal in the atmosphere. In this case, it's not the Raman scattering, but it's the Rayleigh scattering. And in order to distinguish the Rayleigh signal from the particulate backscatter, you need the high spectral resolution. So therefore, it is called high spectral resolution LiDAR. So you can distinguish the molecular from the particle backscatter in the atmosphere. And similar to the Raman LiDAR technique, you can measure extinction and backscatter independently, and in this way measure the LiDAR ratio directly. And in contrast, is shown here the Calypso technique, or the technique that has been used for Calypso is the pure backscatter LiDAR operating at 532. And if you want to make the retrieval for the backscatter or extinction coefficient, you need the LiDAR ratio as an input parameter in the LiDAR equation. And this ends up in large uncertainty, as we can see here. What we expect for the backscatter coefficient, we can derive from the high spectral resolution LiDAR with very high accuracy, the backscatter and also the extinction, because they are measured independently, while with the unknown LiDAR ratio as the input, this arrow accumulates towards the ground as you measure from space, from top. The uncertainty becomes larger and larger as you go towards the ground, and especially for the extinction measurement, which is the most important measure to understand the latest properties of the aerosols, you get a very large uncertainty. So, and therefore, the HSRL technique is so important for the aerosol measurement. So we have seen this before, but now we understand that it is important to know the aerosol types if we want to retrieve aerosol properties from space. And you see now that this plot, LiDAR ratio versus depolarization ratio, is an important input for EarthCARE, because we can use it to define the aerosol classification for the spaceborne LiDAR. So we can use this knowledge and define like smoke and pollution and marine and dust and their mixtures and use it in the retrievals of the spaceborne LiDAR. So we need the classification. We need it also for the radiative transfer calculations, because we need to know the aerosol type to do radiative transfer calculation for the atmosphere. And we need this knowledge also to study aerosol cloud interactions, to know whether, for example, these particles can act as cloud condensation nuclei or ice nucleating particles. And also we can use the information then for model evaluation and data assimilation. So the classification is a very important thing. And what we did for EarthCARE, we used these ground-based observations as an input, and then we tried a microphysical description of these particles, and you can, with a very easy attempt, define a microphysical size distribution together with the reflective index, and the smoke small particles. So this is the fine mode and has a high absorption, so they are strongly absorbing. The pollution is also a fine mode aerosol with moderately absorption properties. The marine, as I said, is a coarse mode. It's usually around 1 to 2 micron in size, and is in principle non-absorbing aerosol. And the after dust, which is the non-spherical particle in the coarse mode with a moderate absorption. And by using this microphysical description, we can also develop a parameterization for the radiation properties of the aerosol. So if you use these 4 components and you mix them, you can calculate theoretically in terms of this diagram, Lidar ratio versus particle linear depolarization ratio, what Armstrong exponent do we expect in which part of this diagram? What is the single scattering albedo? So this means what are the absorption and scattering properties of the aerosol, and what is the asymmetry parameter? This means the large particles scatter a lot of light in the forward direction, whereas the smaller particles scatter more into the sideward direction. And this is the information you need for the radiative transfer calculation. So if you measure from space the Lidar ratio and the particle linear depolarization ratio, then you put it in this diagram measurement point, and then you can directly take the information from this model and translate the Lidar ratio and depolarization information into the information of the radiative properties, and then you can do the radiative transfer calculation for the atmosphere. So this is the idea behind the aerosol classification. So now let's come a bit to EarthCARE. EarthCARE is the Earth Cloud Aerosol and Radiation Explorer. It is designed as a multi-instrument platform in order to investigate the role of aerosols and clouds and improve our knowledge on their role in the Earth system. We observe cloud profiles. We observe aerosol profiles, type resolve, and we observe solar and thermal radiation. And this is done with 4 instruments: size, spectral resolution, LiDAR, UPLIT, the cloud profiling radar, Doppler with Doppler capability, CPR. We have a multispectral imager on board and the broadband radiometer. And there is a big observation goal. We want to understand the atmosphere so well that we can get the radiative closure at the top of the atmosphere within 10 watts per square meter. It means as we measure the cloud and aerosol profiles and we do a radiative transfer calculation and calculate what radiation do we expect at the top of the atmosphere, then we can directly compare it with the measurement of the broadband radiometer and check whether we have understood well what the 3-dimensional behavior of the atmosphere is. So yeah, this is EarthCARE. It's also called the White Dragon or Hakoyu in Japanese. So it's a joint ESA and JAXA development, and the system has platform has been launched on the 29th of May last year. It was a very, very exciting event for all of us who were involved in the development over a very long time. Some impression from the launch, how the rocket was brought into space, and we were watching this event in the European Space Observation Center in Darmstadt in Germany with many people from ESA and from the science community involved. So it was really a very impressive and very exciting moment when the countdown reached 0, and then yeah, we all stopped breathing. About 10 minutes until the platform was released and was free to fly in the space. About when the platform was released from the second stage of the rocket. Yeah, so we were very lucky, and about 1 hour later, also the first signal was obtained, and then it was clear that also the solar panels had been deployed, and the platform was in good shape and communicated with the ground. So we had really time to celebrate the successful launch. So you can watch this on YouTube, the whole launch event. So now let's go a bit deeper into the instrumentation. We have the cloud profiling radar. This is a high power 94 gigahertz Doppler radar. It's the first time that we measure Doppler velocity with the radar from space. The big antenna is 5 meter in diameter. And we have here on the right side the upright instrument. You see here is look into the telescope. It's a 60 centimeter telescope. We have 2 outlets for the laser beam. So we have 2 lasers on board. Yeah, the repetition rate is such that we get a horizontal sampling of 280 meters, and we have 3 signals: the Rayleigh signal and the Nico and phosphor signals. Multispectral imager gives us an idea on the horizontal distribution of aerosols and clouds, so it gives us a kind of context to understand also the 3-dimensional distribution of the clouds and aerosols, not only a cross-section that you get from the LiDAR and from the radar. Really are with the different, the short wave and the long wave observation channels. So now we were very lucky. We were waiting a couple of weeks or a bit longer for the different instruments to see whether we really get good data. And the radar was switched on the 13th of June, and we saw the first radar measurements that were in a big collective system with snow and ice crystals and rain in the lower part. You see the fall velocity. The rain is falling faster than the snow and the ice in the upper part of the cloud. So this already gives us confidence that the radar is working well. Then we have the PCR switched on the 18th of June, also showing nice measurements of cloudy systems here in the different channels. MSI was switched on in July after for the optical instruments kind of decontamination period. We see nice images here of a thunderstorm above Italy. So it was published as the first image of MSI. And finally, the lasers were switched on in the beginning of August, and we got the first LiDAR data on the 2nd of August. And here's an example: stratospheric clouds and other clouds over Antarctica. So we were very happy after these, about 8 weeks or so after the launch, that we could see that everything works very well, and we could start with the evaluation of the data and the validation and so on. Behind EarthCARE, there is a very complex production chain where the data of the 4 instruments flow in, and then we get the different geophysical properties from the different instruments. This is then called level 2A data, like the radar only data, the LiDAR only data, and so on. And when this is all done, then we can also combine other information from the different systems and can, for example, combine target classification, combine cloud and aerosol profiles from the LiDAR and the radar. And this goes further on into a 3D scene construction of the atmosphere, which is then used to do the radiative transfer calculations and produce the radiative products, and then goes into the assessment against the DDR measurement and the closure. So we can read this in the different papers. These algorithms have been developed by a large scientific developer team with several institutions involved. So different institutions are responsible for the different products you see here. And we have more than 30 papers already published in our EarthCARE special issue on the level 2 algorithms and data products, where you can find all the details on these very complex production chain. I will show only one very recent example to bring us back to the aerosols and the aerosol typing. So this is an example of an atlas cross-section. This goes across Canada. Here you see the Hudson Bay in the left and the Great Lakes in North America here in the right. We have a lot of wildfires in northern Canada since the spring, since April, May. This is a measurement done on the 1st of June. And what we can see here is this layer up in the stratosphere, and this indicates a big pyrocumulonimbus convection. This means this is the big thunderstorm cloud produced by the large fires, which bring the smoke very fastly high up into the atmosphere. And the magenta line indicates the tropopause, and you see that this smoke layer there is going up to like 14-kilometer height. So very high, and also there are a lot of other layers around stemming from these large wildfires in Canada. And then we can see how this distributes over the whole northern hemisphere. You can see a cross-section here. This is from the 6th of June over Europe. It starts to the left, almost over the North Pole. So it goes over the Arctic region, and then Scandinavia, down to Central Europe, down to Italy here. And you see that it is full of aerosols, but also clouds here in the cross-section, all these greenish and orange layers. This is smoke that we see in the upper troposphere and lower stratosphere. You see long red stratospheric layer reaching up, in this case, up to about 17 kilometer height. Here as well. So here is the light scale. It's about 17 here, and this also shows that the smoke further increases in height. This is due to the absorption property. So the smoke is heating its surrounding, and then the whole air is lifted over time. And we see these smoke layers in the stratosphere going up then up to 20 or even higher kilometers. And you also see that there are ice clouds embedded. So the colors that are more dark red and black, indicate the ice clouds that form in these dust layers. On the left, you see the fourth color image, with an idea on the atmospheric column showing the ice cloud with the bluish color, and the water cloud with the reddish color. So this is the kind of information you can get, and this brings me back to the research on wildfire smoke that we did over the last 10 years or so. Starting in 2017, we saw an increased load of wildfire smoke in the atmosphere in many parts of the world. We had large fires in Canada and California in 2017, and then followed in the following years by other large fire events, and you have heard about these fire events certainly. And I go into a bit more detail of these different events here. This is 2017, and this is the photo I have taken in August in Germany. And we were on a bicycle tour, and the sun was already below the horizon in the evening, and suddenly we saw these colored structures in the sky, and with a little bit experienced eye, you see this cannot be clouds. You see these wave-like structures and these very, very long stretch layers, and so this indicated also at that time that the layers must be very high in the atmosphere, so I estimated about 15-kilometer height maybe, and indeed when we did then measurements with our poly system in Leipzig, we found this layer between 15 and 16-kilometer height in this week in August 2017. So this was one of the first observations we made of these stratospheric smoke layers, and we started looking closer in this kind of aerosol. So these very large wildfires in 2017 is similar as in this year. They are brought into the stratosphere and then they remain for a very long time because there's no weather in the stratosphere. There's no precipitation that can remove the particles. So they last there for a very long time. And with our LiDAR network in Europe, where you see the Central European stations in green, and blue is Southwestern Europe, and red is Southeastern Europe. And then you see the measurements here in the same color scale. You also see that these layers are lofted. They go above 20 kilometers in time. The aerosol optical depth is high in the beginning and then decreases exponentially, and the extinction coefficient in the center of mass of this layer you can also determine. And as you know, this is smoke, you can also convert the extinction coefficient into a mass concentration. So this kind of information we get also then from the network measurements where we have more stations contributing and not only a single observation. We have seen also very strong smoke events in the southern hemisphere, and some of you may remember the strong Australian forest fires in the end of 1919, beginning of 2020, when a large smoke plume developed in the stratosphere and was transported over the Pacific Ocean. At that time, we had our LiDAR in Punta Arenas in southern Chile, and this smoke plume was so dense and that it initiated its own circulation. So it was like a little cyclone in the stratosphere, rotating and moving across the Pacific, and then we could see it at a certain time also over southern Chile, and we could see the increase of the layer over time. You see this rose up to almost 30-kilometer height over time, and this is a measurement from Calypso, which also measured this plume, observed it over several weeks, and this is an example where we observed it at the same time with Calypso over Punta Arenas, and as it indicated with the ground-based LiDAR, and this is based on LiDAR. Another interesting case are these Siberian fires, where the smoke is not directly injected up into the stratosphere, but there is a lot of smoke in the troposphere, and also there a lofting process occurs. So also here the smoke fills the atmosphere up to the tropopause over Siberia, and finally over the Arctic. So we made these observations during the mosaic campaign in the Arctic region later on, and from those measurements, in the end, we concluded there are two major lofting processes going on. So one is this pyroconvective lofting, where the aerosol is directly injected into the stratosphere, and one is this self-lofting process caused by the absorption of solar radiation, with the slow lofting within 3 to 7 days in the troposphere up to the tropopause region. And this is, of course, very important to know that we have this kind of aerosols. They are a little bit different in their properties depending on the lofting process. If they have time to be processed in the troposphere, or whether they are partially injected into the stratosphere and then immediately freeze in the cold temperatures up there, and then they also show depolarization in the stratosphere. So this is an important field of research to know how they can influence cloud formation, for example, in the upper troposphere. And this is something we investigated also here during our 1-year Arctic campaign, where our OceanNet atmosphere platform was placed on the Polarstern research vessel, and the vessel was frozen in the ice and then drifted with the ice over the Arctic winter here from October in the Arctic winter, just drifted with the ice flow. And we made continuous measurement over this period and could see a lot of aerosol and cloud formation in the Arctic. So impressions from top, seeing 2 green beams. One is our TROPOS polylidar beam pointing 5 degrees of Celsius, and the other one is from the US ARM ACTRlS LiDAR. So they were placed next to each other. Yeah, and of course in Arctic winter, everything is dark over months, and the people have to live there in the darkness. Another view how all these containers were placed on board of the Polarstern with the OceanNet polylidar. Green light here coming out of the container. We also had the radar systems of the ARM side on board, so we could also do a lot of LiDAR and radar synergy investigation. Just an example here, what you see in the Arctic, 4th of February 2020. There are a lot of aerosol layers, Arctic haze in the lower part of the troposphere, and then the wildfire smoke layers around the tropopause region, upper troposphere, lower stratosphere, and above there were also polar stratospheric clouds developing, and some cirrus clouds are seen here as well. So we did not expect that we see such a high aerosol load in the polar region. So usually common idea is the polar regions are very clear and you shouldn't have much aerosol there, but indeed in the polar vortex in winter, a lot of aerosol is captured, and especially since we have these large wildfires in northern Canada and Siberia, so around the Arctic region, a lot of smoke is transported and then captured there over the winter, can be processed there and influence the atmospheric properties and the cloud formation. And this is an example then where you have the smoke layer, but also the cirrus clouds developing. And here we nicely see that the ice formation starts in the smoke layer at 10-kilometer height, and then once the ice crystals are formed, they start to grow, and then they start to fall when they are larger. So you see these fall streaks, but the generation itself is in the smoke layer. So it's a nice example of heterogeneous ice formation. It means the smoke particles really act as ice nucleation particles here. So from numbers, we could determine the surface area concentration of the smoke particles, like 5 to 15 square micrometers per cubic centimeter. We have ice saturation of 1.4. This indicates that we have a heterogeneous ice formation here, and from the radar measurements, we could determine that we have just a very low ice crystal number concentrations of 0.01 to 10 per liter. So this is a typical number for the heterogeneous formation. If you would test a homogeneous formation of ice crystals, which take place on the liquid aerosol particles, phosphoric acid droplets, then you get like 100 to 1,000 ice crystals. And then we use this information to get some more idea on the PCN and INC properties of the aerosol. So when we have the classification via the depolarization information and the LiDAR ratio information, we can classify the different aerosol types, and together with microphysical information for these different types of aerosols, which we get from AeroNet columnar measurements, we can determine some kind of transformation from the optical properties into the microphysical properties, and then finally derive concentrations of PCN condensation, cloud condensation nuclei concentrations, and some parameterization we use from chamber observations can also estimate the INP number concentration. This is the number I showed you before. So there is the whole retrieval scheme behind with some parameterizations. But everything is based in the end on the aerosol classification, and then we can apply these factors to estimate like surface area concentration and number concentration for these different types of aerosols. Okay, maybe I go a bit faster here. We have this combined retrieval scheme. So if we go now from the pure aerosol retrievals into combined LiDAR radar retrieval, so we have to combine the information from the LiDAR and from the radar. We can make use of the Doppler information to get an idea on the size of the falling particles, the cloud hydrometeors, and then we can combine all this and come up also with cloud properties. So we have developed this algorithm where all the information from all the different inputs goes in, and then we have the different retrieval schemes for the LiDAR, for the radar coming from the polynet chain, and cloudnet chain for the radar, and then we can combine it and come up in the end with different variables characterizing the aerosol and the cloud properties and the radiation properties. I won't describe that in detail. Just some examples what we can do then with our LiDAR system. So we can observe the clouds. This is also a measurement from the Arctic. We see these persistent liquid layers that we observe in the Arctic. So it was for a long time not clear why they can persist for such a long time, because all the time there's also ice falling out of these clouds, and they always have to be newly generated by a little bit of lifting of the cloud, so to maintain the supersaturation, so that the droplets can develop again and again, even if they freeze and fall out of the cloud as ice crystals. And to use here our dual field of view method to determine cloud droplet number concentrations and cloud droplet effective radius. So we see a constant concentration of about droplets per cubic centimeter with an effective radius of 5 to 10 microns, so which is very typical for like an isochromal water cloud. So I mentioned for this kind of measurement, we apply a dual field of view technique. This means we look into the atmosphere with the different fields of view with the LiDAR, and you see in this principal sketch that as soon as you hit the cloud, the forward scattering is increased, and the peak in the forward scattering increases. And then if you measure with the different fields of view, you can get an idea on the size of the particles. So this is published by Christopher Jimenez of our group. And these dual fields of view measurements are implemented in many of our poly systems. Meanwhile, to support the aerosol cloud interaction studies. So this is more or less a direct measurement of the Toomey effect we can make, because we get the aerosol properties and at the same time size of the droplets in the cloud, so we can directly investigate the aerosol cloud interaction according to the Toomey effect. And we have done this in different places, as you see on the map here, such as two examples showing the number concentration of the CCNs versus the number concentration of the droplet. So you can directly relate how many condensation particles do you have and how many droplets do you get. And make a regression for that and determine the so-called aerosol cloud interaction index, which is the number in the top left. So we have for the Punta Arenas, we get a high index. This means the aerosol strongly influences the properties of the cloud, whereas for the northern hemisphere, here at this position base, we don't have such a high index, because there are always a lot of particles in the atmosphere, and doesn't matter if you have a bit more or a bit less, there are always sufficient CCNs in the atmosphere to influence or to form a cloud droplet. And similarly for the ice crystals, when we combine the LiDAR and the radar measurement, and we can measure the fraction of ice-containing clouds in different regions of the world, and look whether the particles influence the ice formation in the cloud. And what we see is this clear difference between the northern hemisphere, where we have the measurement of Leipzig and indicating northern hemisphere, and we have the measurement in Punta Arenas in a very clear southern hemisphere. And you see that in this range between 0 and minus 15 degrees, where we can only have heterogeneous ice formation, we need the presence of ice-creating particles to form ice in water clouds, to make a mixed phase cloud. And so we have here a much higher fraction of ice in the cloud in the northern hemisphere locations compared to Punta Arenas. So we can also determine the number of ice-containing particles per liter. Here higher for the northern hemisphere than in the pure marine boundary or marine troposphere. This would be a very, very low content. If we assume a little bit of continental aerosols come closer here, but still there are not enough INT in this clear atmosphere to produce a lot of ice formation in the clouds above minus 15 degrees. So this is the message for the aerosol cloud interaction. And I guess as a, sorry for my long talk, as a final message, I would like to come also to a new methodology that has recently been implemented in several LiDAR systems, also in the ACTRlS network, and also we do it now in our poly system, and this is fluorescence measurement, because yeah, we now have all this smoke in the atmosphere and also other biological particles, and sometimes it is not so easy to distinguish the smoke, for example, from a pollution aerosol. But fluorescence measurements can help because everything what is of biological origin tends to fluoresce in the atmosphere. You see some examples here for different kinds of bacteria or other biological material, pollen, for example, in the atmosphere. That gives you a fluorescent spectrum. And if we work with our typical Earth nanometer and we put another measurement channel, for example, in this region or in this region, we can check whether we get some signals here, which you see from Raman or other together. So we can do this just with an additional filter in this wavelength range, or you can even put a spectrometer there to measure a whole spectrum of the fluorescence. And this gives you a very nice measurement. So I didn't believe that in the beginning, but if you look at the measurement, this is the normal range-corrected signal at 1064 nanometers. So you mainly see the cirrus cloud and some aerosol layers, very faint layers. And then you look at the next time in the fluorescence. Different picture. And this shows you all the layers of biological material present in here. Smoke layer here, for example, you see maybe other smoke, but also biological material in the boundary layer, pollen and other kinds of remnants. So you get a picture of the biology of the atmosphere by the fluorescence measurement. And you can see that it can measure this signal even within the cirrus cloud. Yeah? So usually if you have a cloud in the LiDAR signal, we don't see the aerosol anymore because the backscatter is completely dominated by the cloud particles. But with the fluorescence measurement, you see the smoke layer, and we see how the cirrus form again in the smoke layer. So it's again there was a trigger by the smoke particles here at the Tropospheric region. It gives us very new opportunities to study aerosol cloud interactions in the atmosphere. So indicated again here with this ellipse, which shows the same region in the upper and in the lower picture. So you see that the smoke layer is on top of this cirrus cloud, and the cirrus cloud formed in this smoke layer. Yeah, so this brings me to the end. So what are the take-home messages? With our advanced network and satellite-based LiDAR systems, we can really provide a detailed view of the global aerosol distribution. We have seen that aerosol tracing based on the intrinsic optical properties is the key to study aerosol cloud interaction and to do radiative closure studies. So tracing it always comes first before you do anything else with the data. And the nice thing we can do from ground, but also now from space with EarthCARE is the synergy. So we can couple the LiDAR and the radar observations together with passive observations. And we can also from ground apply the new methodologies like the dual field of view and the fluorescence measurement to really study interactions between aerosol cloud precipitation, radiation, and dynamics. I mean, we have to come closer. We can measure aerosols, we can measure clouds, but the actual interaction studies, this is the core where we need more understanding, and so where we can only come with new methodologies and with new synergies, we can come closer to really quantify how much aerosol impacts the formation of cloud particles and precipitation. And I think what I also made clear, smoke is nowadays a largely unknown player, and it's obviously increasing due to climate change. We see a lot more fires all over the world, and the smoke is omnipresent meanwhile in the atmosphere.
and especially if it goes high up, it's hardly to be removed. Yeah, I think it can really play a large role also for the radiation budget, not only via the direct, but also via the indirect effect of influencing the ICR. So, and we do have EarthCARE data available, so they are public. Everybody can use them and do such kinds of studies. So feel encouraged to work with all these very impressive, interesting data. Thank you.
So that make it into your answer. I think we could take a picture for it again. So thank you. Online audience, yes, comment. 37,000 1,500 audience online. I think we have time for something.
The very basic approach, and especially for Raman measurements, this is not easy. And usually we measure at nighttime because the signals are so low. So high spectral resolution is better because the relay is higher. Get a better signal to noise ratio in daytime. Also true from space. Of course, we have always to average a little bit horizontally, vertically, to get a good signal to noise ratio. So this is the very basic uncertainty we have. Yeah, and then we have to take care of all the systematic errors we can make. Yeah, so I think with the Raman and high spectral resolution LiDAR methods, we are on the safe side regarding input parameters. So we don't need an estimate on LiDAR ratio or something else. We just need a good estimate of pressure and temperature for the retrievals. This is usually not a big issue. And then, of course, you have to take care of the systems, that they are well adjusted, that our overlap is well adjusted, that we don't have any temperature influence in the container, also that the laser beam makes like this. Yeah, there's a lot of control behind. Yeah, what you need to avoid any kind of biases in your measurement. But I think after 20, 30 years of experience, this is well done. But never forget to put arrow bars on your measurements. Of course, the right message, yeah.
Yeah. That's it.
I have a problem. Yeah, we are curious about the aerosol in the Antarctic area, especially in Greenland. So I have a question that our laser talk is can provide with a profile of the aerosol. But the data point is first in time domain and the spatial domain. So we are curious about the time scale and the spatial scale that we can consider the measured value is uniform. Yeah.
Yeah. I mean, this is maybe not easy to answer, but also here the advice can be make use of the spaceborne data to look at the representativity of your measurement. Yeah, I mean, usually, okay, the mass is transported across the ground-based site. So if you look there for several hours, several days, or several weeks, you get a good representation, but you will maybe need like backwards trajectories to see where the airflow comes from and what you really cover in your measurement and how representative it is for the entire Arctic region. But with the spaceborne LiDAR, we have now a much better idea even. I mean, from space, we don't see so much details, yeah, but you see the larger scale coverage of the aerosols, and from ground, we have a much better view into the details, into the processes, so we can do process studies and so on. So combining the two views from ground and from space, I think, is very helpful to get the idea on the regional and on the global scale. This would be my answer.
You asked for a break for.
Oh, I'm fine.
Okay. Any other questions? Yes. Xiaoying, please. Yeah. After this one. Yes, please ask.
Thank you, sir. Thank you very much for the very nice presentation, very impressive. I'm working on the Doppler LiDAR of the simultaneously measurement of wind and precipitation parameters. So I'm very interested in your field campaign, which involved the micro radar, spectrometer to DVD, and particle spectrometer.
Yeah.
And so my first question is, what role did these instruments play in the overall campaign? My second question is, which ring parameters from these ring instruments were compared and analyzed with the LiDAR data?
Yeah, this is very, very important question, and I did not go into the details of this kind of research because this is the entire new topic I can talk another 2 hours about. It's very, very important to measure the dynamics together with the aerosol if you want to study cloud. Yeah, so you need to know about the vertical movement in the atmosphere. This is very important. And so we apply the Doppler LiDAR and also the Doppler radar. And we look strictly vertically to see the vertical velocities. So we can see with the Doppler LiDAR, for example, you see the vertical movement in the boundary layer. So you see which kind of air goes into the cloud and where you have maybe downward mixing of clear air into the cloud. So this is important also when you want to study the Toomey effect, to really see the parts that are influenced by the aerosol. This is what we did to distinguish between the updraft and the downdraft, and then look at the cloud properties in the updraft and in the downdraft. So it gives you a deeper insight into the Toomey effect. Then, of course, we need the vertical velocity of the whole system. If you go into precipitation studies, I mean, precipitation is of course strongly influenced by vertical movements, yeah, and it's very difficult to disentangle what cloud properties are indeed influenced by particles and what is, I think, much stronger influence of the dynamics in the cloud. Updraft and downwards within updraft and downdraft within the cloud. Yeah, so a lot of mixing processes going on. So the Doppler radar is also very, very important. And then, I mean, horizontal wind information is also needed. So what we do is maybe once or twice per hour we do a conical scan to also derive the horizontal wind velocity from the LiDAR and from the radar. So this is like a systematically done, just implemented in the measurement routine. What else can I say?
disentangling aerosol and dynamics effects is important. Do you have any specific questions with that? I'm not so much an expert in this, but we have a group in our department working on these effects.
I have some comment. Xiaoying just doing the research to study the spectrum of the coherent LiDAR, because you do have a wind and droplet speed, you have to pick or mix the pick. So we want to retrieve also the rain droplets just based on that. So
Yeah. I mean, this is what I just forgot to say. Maybe I can go back.
Yeah, for sure.
Or-
要点一下那个屏幕分享啊。还弄完了。OK， 你把那个确定的那个，这个要。
Distinguish different kind of particles in the Doppler spectrum. So
Yeah.
faster falling particles, slower fasting, and then you can also get from the falling velocity, you can get an idea on the size distribution. So this also goes into this retrieval that you get an estimate on the particle size via the falling velocity. So this is quite complicated scheme, but you have a lot of information in these spectra.
Okay, any questions? Yeah, comments. Yeah, actually, I hold this question for a long time. Then I have a opportunity now to ask. So for the aerosol classification, yeah, I just I think I keep in mind for the light ratio and the little ratio, and with the different aerosol types, with the cluster of the different types. So how when we first measurement these cases, how can we identify with a ground-based identify the aerosol type for the ground-based measurement?
So as long as we do not know about the relationship, do you mean?
Yeah. How we do this, know this relationship?
Yeah, of course. I mean, long-term experience, lot of backward trajectory studies to see where the aerosol layers originate from, so that you clearly know. I have this layer with the backward trajectory. I see this is locked into the atmosphere at this point in the Sahara Desert, for example. So really make a source analysis, a source attribution for all the layers you have, and classify them in this way first, and then see which optical properties they have, and then in the next step you can use the optical properties to classify. Which is, of course, you need the long-term measurements in all the different regions, to get this idea.
Do we need some other measurements, like scientific measurements, to verify this, or?
Also, I mean, in all these field experiments, there were also airborne measurements involved. So we have since maybe 2006, we made campaigns in the Sahara, in the outflow region, Cabo Verde, Barbados. We always had the Falcon aircraft involved. They did in situ measurements, so we got the particle size distribution. We did it in the Mediterranean, in different regions. So we are quite confident, and we also, I think Atina in her paper, she showed also comparison between in situ measurements of for the measurements I showed from Cyprus, where we really compared our parameterization approach, just assuming a coarse mode distribution for the dust, and then comparing this with the in situ measurement. And surprisingly, it fits really well. Yeah. So, but also, I mean, these parameterizations, they come from long-term AeroNet observations. Yeah, you have like 30, 40 years of AeroNet observations all over the world. And if you select the observations from very characteristic places, like desert places or marine places, and you average over a number of observations, get a mean size distribution in the column. If you are sure you have just this one aerosol type present, you get a clear idea on the mean size distribution of the marine aerosol, of the desert aerosol, and this is what I applied then also in this classification scheme for ACTRlS, that I just took this from what the people said. This is the mean distribution for sea salt aerosol, for dust aerosol, and yeah, and we can use this and say these are the mean radiative properties.
Thank you. Please. Thank you for your presentation. I am a doctor from Mr. Wu's team, and I'm currently focusing on the spaceborne counting LiDAR on the altimetry area. And from my experience, and not only for me, but also all over the world, young scientists have found the interesting phenomenon that the data from the counting spaceborne LiDAR, the theoretical signal and noise value have a big difference from the actual value, which means that there may be some scientific problem or engineering problem in the LiDAR systems. So my first question is whether you have experienced such an unusual or interesting conditions when you handle and process the satellite or ground-based LiDAR systems. And my second question is, do you think whether we can use the photocounting LiDAR in the future, the aerosol or cloud ground-based or spaceborne LiDAR systems in the future? Thank you.
Yeah, I mean, it's also an interesting question because I myself also did a lot of simulations for the ground-based and also for the spaceborne LiDAR. And for our ground-based LiDARs, I also found this effect that usually you have a factor of 10 less signal than expected. If you just put the theoretical values in, like laser energy and the optical efficiencies and the detection efficiency, then you think maybe for a Raman LiDAR, you should have like 30–40% efficiency of the system. But in the end, you see like 3 to 10% efficiency. So this is just, yeah, a lot of losses in the system, obviously, which you do not consider in the simulation. Surprisingly, for ACTRlS, this is not the case. So we have the EC7, the EarthCARE simulator, and we have worked with the simulator over the last 15 years to develop the algorithms. So we have produced artificial atmospheric data with realistic noise, and then develop the algorithms in a way that they can handle the noise. And when we saw the first data from space, we were of course curious, yeah, how will they look like? And they look better than the simulation. So we were really surprised how good the signal-to-noise ratio for the ACTRlS LiDAR is in space. So we did not see this effect that we get much less signal. So obviously the engineering, the design was so well done, and the values they gave us to use in the simulation were so realistic that they really meet the expectations. And of course, there are strong requirements for the industry, for the efficiency of the instrument, for the instrument parameters, and they also tested it on the ground, and then they could prove that they meet all the requirements, and this is what we see in the data in the end. Yeah. So yeah, yes, I think our homemade LiDARs maybe they are dusty and whatever, not so perfect, but the spaceborne system is really well done.
Yes, I agree. Yes, the simulation, we cannot have an ideal simulation. instead of you should include so many real scenario observations taking into account, then you have that. So I do have a question, actually. You mentioned the smoke and also the optical properties used in fluorescence LiDAR. So as I remember correctly, I think the TROPOS has in IRIC in Romania, I think the public or introduced the first fluorescence LiDAR and won the best young oral poster at that time. I think the fluorescence is from organic or biological contributions, maybe from pollen or something like that. So I always curious about that. So many pollens?
No, it's not the in the smoke. It's not the pollen. It's just the organic material.
Yes.
You should. I mean, many people think that smoke consists of soot, but this is, soot is a very small contribution in these smoke particles, and most of the smoke particle consists of organic material. So this is now what we also see, and why we observe these different optical properties. So you clearly see this when you bring the particles into the stratosphere, they freeze.
Yeah.
So, and they get glassy. And this is what the chemists tell us. Yeah, this is organic material which gets like amorph, a bit glassy, and then you get the non-spherical shape, and you see the depolarization in the stratosphere at the low temperature and the low humidity conditions. And this organic material shows fluorescence strongly for fluorescence.
Yes, from your talk and the recent publication, I noted that the smoke is the big input for that fluorescence.
Yeah.
And actually, if it does not truly burn, the fully burn is carbon, right? No fluorescence.
Yeah.
Some not fully burn or should be have some fluorescence effect. So my question actually is just like we measure the aging of aerosols, can we use optical measurement like measurement to to observe or monitoring the process from maybe different stage of this burning effect or how this became clear of this cloud?
Yeah, different things. First of all, the kind of fire has to be considered. Yeah, if it is a really flaming fire or a smoldering fire, this makes a very different. You get black smoke or white smoke from the different kinds of fire. So this is already a different optical properties from the kind of fire. And then during the transport in the atmosphere, you have processing. And I guess Vasilis has published a paper already 20 years ago or so, Vasilis Amerides, where he showed the aging effect in the optical properties. So yeah, I mean, these particles are really, they are processed in the atmosphere. They are chemically reactive. And there's also condensation, I guess, of gases on the particles. Maybe you have also with the fire a lot of gases emitted, and then you have secondary organic aerosol formation in the plumes, and then you have in the troposphere during transport you have humidity effect. So the particles usually grow during transport in the troposphere, and then also they get more spherical. So we don't see dipole in the troposphere, but we see a lot of dipole in the stratosphere. So because then the processing is stopped in the stratosphere, there's not much.
So the following question about this smoke, time defect, because from your observation, their list is so high up to 20, 25 kilometers, like permanent layer. I don't know whether it's going, but just go up to space.
I know. I mean, it depends on the optical depth. Yeah, you need a certain optical depth to have the effect of lofting, to have sufficient heating that the layers can be lofted. So if the aerosol is spread out, then it stops. Or lofting gets slower and slower. So you have a thick plume in the beginning, really pushed up within days. But if the plume is diluted, then the effect is stopped.
But there is no precipitation at so high altitude, so they will be stayed for a very long time.
Yeah, they will stay and can only participate itself. So or have other kind of process. I mean, we also think about polar stratospheric cloud formation, and if we have new chemistry. So chemists also say we don't know what's going on if we have to consider a completely new chemistry for ozone depletion, for example. to play a role in the PSC formation, to play a role in the ozone depletion. This is what we thought. So we have done some studies correlating ozone concentration with smoke concentration. So you clearly see a dependency. And yeah, maybe we have to rethink the stratospheric ozone chemistry with all this smoke influence.
Yes, because I think we should recheck the ACD of measurement at that altitude, because we already see some residual aerosol with a strong lidar ratio, but more polarization. We thought at that time it's some residue of Tonga volcanic eruptions, smoke, but I'm not sure. Maybe just they should just check the source.
Yeah.
Smoke.
Yeah, of course, we have to distinguish also the volcanic aerosols from the smoke aerosol. It's very important. We had several eruptions. You see the volcanic aerosol from the Mount Huon eruption in the satellite data all the time. Yes. Again, classification.
Classification. Yes, of course. Thank you. Any other questions? 线上有问题吗？
有一个刚刚好像
Okay, we may have one question at least from online meeting. How? 没有吗？ No? Okay. Okay. Now, I think we should thank Ulla again. Yeah.
Many people who are behind all these investigations, our TROPOS teams, the EarthCARE team,
Yeah.
the active community.
Oh.
So it's a large community behind all these.
Actually, this is the biggest infrastructure for cloud there. So, so any young scientists who would like to join that discussion?
Maybe we stay here for a while and people can contact me.
Yeah, for sure. 好，我们现在没有什么问题的话，大家自由活动了。如果还有什么这个问题想单独交流的话，我们可以就过来，咱们就交流，好不好？其他同学可以待会参观。